questions too. All right. Hello.
Hello.
Dr. Ruppert? Ruppert?
Ruppert.
Ruppert. Your first name is Natalia, is
Yes.
that right?
Mm-hmm.
And you are the lead scientist here at the Alaska Earthquake Center?
Research seismologist.
Oh, so are you thinking about the inside of the Earth all the time?
Not all the time. I have other fun things that I do once in a while.
Thank you so much for joining us here on Facebook Live. People are going to be joining in, and everybody who's listening and watching, if you've got questions, I'm monitoring right here, and I'll be able to answer some of the questions. I'll try to keep the camera as much as I can. The tripod wobbles around a little bit, but that's what we're doing Facebook Live for. The first big questions everybody had, and I was reading a little bit about that, was why no tsunami?
Well, this earthquake, if you look just where it was located, you would think it would generate a tsunami, but for a tsunami, you need some vertical motions. So the ocean floor needs to move up or down to displace all that big water mass to create a tsunami wave. This earthquake was a strike-slip earthquake, so there was very little vertical motion involved, and most of the energy went into horizontal motion. So there was no major vertical displacement of the ocean floor. That's why it did not create a significant tsunami.
Okay, I have someone saying here that they can't hear us. Is that still true? Have you got no audio out there? Post in there if you can't hear. So is this an unusual event in the size? What made it so big?
Well, it was
great.
unusual.
Thank you, Marmin. Someone says they have audio, so that's great. They can hear us.
Okay, it was unusual both in its size and location and type of faults involved, because for earthquake offshore Kodiak Island, we would expect fault that involves vertical motions, either up or down motion, and this was unusual in that sense that it was a strike-slip fault. Although there are no very well mapped or known faults in that area, so this was kind of unexpected.
Oh, do you expect any earthquakes? What earthquake is expected, I guess, is my follow-up.
For offshore Kodiak Island, we would expect something similar to 1964 earthquake, when the large major fault that separates Pacific plate from North American plate, this is where most of the energy are being accumulated as plates move towards each other. So that fault generates major earthquakes in southern Alaska, Aleutian Islands, and similar faults in Japan and around the Pacific Rim. This is what we mostly expect to happen along the Alaska-Aleutian subduction zone. There are earthquakes that are not confined to this megathrust fault, what we call it, but those are less common.
So there's exciting data you're getting from this. It's new sort of stuff. Does it add to your knowledge about earthquakes in general?
Well, it does. Definitely it will add new knowledge to our understanding of earthquakes in general and tectonics in Alaska specifically. Because it's unusual location, unusual earthquake, we will be able to learn lots of new things about how Earth behaves specifically in Alaska and in general.
And that's what we care about here at the University of Alaska Fairbanks, is Alaska and Alaska Earthquake Center. Just a quick background about the Alaska Earthquake Center. How long has the center been around? Why was it even created in the first place?
Well, the seismic monitoring in Alaska began after the 1964 magnitude 9.2 earthquake. This is when first seismic stations were installed by the Geophysical Institute and by the United States Geological Survey. And from late 1960s through present, we've been adding more and more seismic stations to monitor earthquake activity in the state. So right now, we have on the order of 500 seismic monitoring stations across the state. So definitely the data we are recording are much better and much more comprehensive right now than it used to be in the past. Alaska Earthquake Center came into play in late 1980s when it was formally established as the earthquake center with the mission to monitor regional earthquakes in the state and to report to public, emergency services, and government entities.
And outreach stuff like this, talking with people every day who are really curious and excited when earthquakes happen. Fortunately, nobody was hurt. There was no real big damage from this. So this is sort of a fun thing to talk about outside of the science world.
Right, still lots of human effects. Like after the tsunami warning was issued, there were evacuation orders in Kodiak, so people had to get up in the middle of the night. Sirens were really loud. So I think it was still, even though there were no serious injuries, no serious damage, it had a huge human impact.
To people in the communities. So we've got a question about why do these earthquakes have so many aftershocks? Why not just the one and done?
It depends on the type of earthquake. Normally shallow earthquakes like this one was really shallow, about 10 to 12 miles deep. They produce lots of aftershocks. Deeper earthquakes normally don't produce as many aftershocks. So for this event, this is normal behavior that we are detecting, that it's producing multiple numerous aftershocks.
I'm trying to monitor both pages here at once as people are asking some questions, and I'll just sort of ask you a general question about yourself. Were you excited when your text alert went off that such a large earthquake has happened? Does it fire up your excitement as a scientist?
Normally we are excited about earthquakes when we can apply our knowledge to help people to understand what's happening and to be able to look at the data and to relay information to public and officials. But this time, actually, the reason why I woke up was because I received a phone call that the power was out on campus. So this was kind of unexpected and coincidental, but it actually delayed us in terms of responding to this earthquake because we couldn't get access to our computers, to our system for half an hour or so, over half an hour. So it delayed our response, and there was a little bit a time when I actually couldn't get any information, so I didn't know what was going on.
How unfortunate a coincidence that when such a big event happens, the sort of whole purpose of you being here, and then the power is out. It's not something that you could foresee or plan for.
Well, we can plan for it, yes.
And you will, I'm assuming.
Yes, you can install backup power systems, you can install backup communication systems, you can plan for it, but it's expensive when you have redundancy for everything that you have for your computers, for your internet provider, for your power. Unfortunately, yes, very bad coincidence, because when we have a major earthquake, we want to be on top of it. We want to be able to respond right away. We want to be able to provide information to people. And here we were unable to do it for almost an hour, which is really unfortunate.
Well, I admire your composure today, and I know your team is busy all around in these offices all over here getting the information, compiling data, share it. Who do you share the information with besides just putting it outreach on the website? Are there other researchers that have been contacting you today to get some of those data sets?
We coordinate with National Earthquake Information Center because they provide information for the entire United States. So they collect information from regional networks and they disseminate it through their own channels. We also coordinate with Tsunami Warning Center. We had a couple of calls with National Earthquake Information Center and Tsunami Warning Center this morning as we were discussing specifics of this earthquake, size, location, impact, steps, and what we want to learn about it, etc.
When you were able to start seeing some of the data last night, I'm assuming you came in as soon as you could. Were you surprised? Were you concerned that a tsunami might be happening, or did you know right away when you saw the torsion graph? I think that's one of the things that someone had posted to look at to see if a tsunami is going to happen or not.
Well, we didn't know right away because first of all, we look at location and magnitude size. Location is offshore. Size, initially it was reported as a magnitude 8.2. 8.2 is significant earthquake and definitely capable of generating a devastating tsunami. So first we were really concerned about possibility that the devastating tsunami will, move towards Kodiak and Prince William Sound communities. That alarm was later downgraded to tsunami watch because we realized that the type of earthquake with this mostly horizontal type of movements is not going to be capable of generating a very significant tsunami. But it took time. No, we didn't know right away that there was no tsunami incoming.
That must make you feel as a person versus a scientist, like you're so helpless to stop something that could be a towering wave that could be heading towards a community. Really, what can be done about that?
Right, we cannot stop the wave, especially when it's really large. In some places, like in Japan, they built tsunami barriers, but it only protects so far. I mean, the example was this devastating earthquake a few years ago in Japan, where tsunami waves just went over the top of all these tsunami barriers. So it's really hard to stop it or prevent it, but we try to educate public about what to do in case there is a tsunami warning. They need to be prepared ahead of time, know what their evacuation routes, what their safe points, and once they get this warning, then they know what to do. So, unfortunately, today it was middle of the night, so it was kind of bad timing, but people, I think, heeded the warnings and they followed the protocol.
I did see some Facebook posts from friends who live along the coast, and they heard the warning and they did pack up and head out, because you never know. It's best to be safe.
That's the right thing to do. Yes, better be safe than, sorry, or dead.
Yes, very true. Talk a little bit about how an earthquake causes a tsunami, if someone is out there curious about it and they're about to Google it and look it up. Like, is it because, like, when you get in a bathtub and you displace that water, it just sloshes all around and over the edge?
There are quite a few very nice animations that people can Google and look on YouTube. Yeah, so basically for the tsunami, you need the ocean floor to move up, either up or down. So you need displacement of the ocean floor in the vertical direction. So when the ocean floor either drops, it depends on the type of earthquake. It can drop or it can rise. It displaces that column of water that sits on top of the ocean floor, and then that displaced water just starts moving in all directions, and eventually it will reach the shore and it will propagate depending on how large this tsunami wave. It may go really far inland.
With such a huge event of the magnitude that it was, how far away did sensor stations find it all over the planet? Was it everywhere?
Oh yes, for a magnitude 7.9, it was recorded by all seismic stations across the globe. And the seismic waves circled around the globe multiple times and probably still circling around the globe, slowly dissipating and getting smaller and smaller and smaller.
That's pretty amazing, just to think about that wave moving through our planet's crust over and over and over
Yeah,
again.
some people compare it to a bell ringing. You hit it once and then it keeps ringing because the vibrations still move around, propagate around the bell. So the same with Earth. This is one ring, earthquake, and then the seismic waves start propagating in all directions. And depending how large the earthquake is, these waves can travel around the globe for days.
Rang the Earth's bell. I know you've got a lot of work to do. I'll let you get back to doing that just a couple minutes. I have a personal question for you.
Yeah.
How did you get interested in seismology and becoming the scientist that you are today?
Well, when I was growing up, I always liked mathematics, so I was looking for majors and fields where I can apply my, knowledge, mathematical knowledge, and just liked working with the numbers. So geophysics came up as one of the possibilities, so I started learning geophysics, and seismology happens to be one of the geophysical fields, so I got steered towards seismology, and somehow I ended up in Alaska and been studying earthquakes for about over 20 years now.
It's a pretty exciting place with earthquakes happening every day.
Yes, there is never a dull moment.
So would you recommend people be prepared for earthquake all the time? Have a bag ready to go, all that sort of stuff? Find some preparedness lists to get ready?
Of course, especially if you live in Alaska. Alaska is very seismically active, not only in southern but parts of the state and along the Aleutian Arc, but also in central and northern Alaska. So just know what your risks are and be prepared to grab a bag and leave your house in case it starts to shake really badly.
Any word of advice for young people out there who might be starting to think about what they want to do as a scientist in their life?
Well, there are lots of different fields in earth sciences that you can study rocks, you can study magnetic fields, you can study earthquakes. There are lots of different fields in geophysics that people can be involved with. So if you're interested in earth studies, earth sciences, you can start in general earth sciences and then see if you can narrow it down. If you're more interested in looking under the ground or looking at how the earth deforms or something else.
Something will catch your attention.
Yes.
Do you get what's shaken puns all the time? People asking you, hey, what's shaken?
Yes.
Thank you so much for taking some time to talk with us this afternoon. And thanks everybody for joining in on Facebook Live. We'll archive the video and post it on the page as well. Thank you so much.
Okay, you're welcome. No problem.